it uses this evolutionary algorithm and explores its physical body. So it rocks back and forth, very much like an infant or a young child uses or moves its body and explores the sensor motor coordination that its body affords. I believe this is something that Rolf has already talked about in the form of developmental robotics. So again, this project in essence combines development and evolution, but in a different way from the case of the block pushers. So here our robot begins its life something like a human infant, where it has little understanding of its own body, but by moving or physically interacting with the world, it's able to generate sensor motor data and use that sensor motor data to build these self-models on top that explain the sensor motor data. So in essence, the robot performs some action, gets back some sensor data, then takes one of these self-models. The self-model is actuated in the same way. In the simulation, the simulated robot produces simulated sensor data, and then you compare how close the virtual sensor data is to the physical sensor data. And the closer that match, the better the simulated robot must be. So that becomes the fitness of these self-models, right? So that's one thing you need when you're using an evolutionary algorithm, an ability to award fitness or assess the quality of any one simulated robot. So it's able to optimize the fitness of these self-models. Then once it has one that has high fitness, it evolves a locomotion strategy using that self-model and then tries out that locomotion strategy in the real world. So just to conclude then, provide some concluding remarks before I take questions, moving on to slide 16 here. As we all know, robotics have been incredibly beneficial or useful in manufacturing. So most factories in developed countries at the moment are now almost completely automated. The reason why is because these industrial robots are operating in a factory where they're free to perform exactly the same action over and over again. But obviously we would like to try and deploy robots in other environments, other unstructured environments, like outdoor environments, such as a construction site. The reason why we haven't been able to do that, I would argue, is not so much because of technical challenges. As we can see from industrial robotics, we know how to build very sophisticated machines. Rather, the challenge is conceptual. We don't yet know how to build machines that can continuously adapt their mode of operations to the continuous change that we experience here in the physical world. So again, taking another step back, going on to slide 17 here, as we all know, one of the major challenges that we're all facing are global energy issues. There are a lot of different alternative energy technologies that are being proposed. Some are moving from the research to the deployment stage. Although there's a lot of these different solutions, one thing that's interesting that they all share in common is that they involve deployment of a relatively simple device like a wind turbine or a solar panel, but they need to be deployed on a scale of thousands of square miles or tens of thousands of square kilometers, if you think in metric. And it's very, very costly, obviously, at the moment to try and deploy this very large infrastructure manually. So there's a lot of serious talk here in the United States about trying to develop robotic technology that would be able to simply take these devices like wind turbines and solar panels and deploy them and install them over a very large area. So obviously that's several decades away, but like the Industrial Revolution or Henry Ford's idea about mass production, we could imagine trying to automate construction in outdoor environments using robotics that adapt how they deploy alternative energy devices over a very large area. Using this automation, we may be able to scale up infrastructure. And so that's something obviously for the future. But just to step back now, this is my last overview slide, and just to summarize what I've talked about. I've shown you a robot that is able to exhibit a particular kind of adaptation, which is resiliency. It does that by using an evolutionary algorithm to create self-models from sensor motor data. It then uses those self-models to internally rehearse behaviors before trying them out in reality. Obviously, we don't want to run an evolutionary algorithm directly on a physical machine because evolutionary algorithms require evaluations of hundreds or thousands of trials before you get something that's useful. And it turns out that by doing this, a robot can automatically recover functionality